They will start. Okay. You remember yesterday we were discussing about how the symmetry is realized, right? And then we just argue that it cannot. It's the vector part of the vector symmetry is realized like Wigner whale. However, the axial symmetry is not realized in this manner. And why is that? Because, okay, for the vector symmetry, we see that the hadrons are classified in SU2 or SU3 multiplets, right? For instance, the pions, we have the octet of, okay, that's great. We had the octet where the pion is included with spin parity 0 minus. They are very light. The pion mass is 140. And in the same multiplet, we had kaons and antikaons, that which masses are the order of 500, more or less, works. There was also an octet of nucleon, where the nucleon lives, okay, containing the nucleons, the sigma, the lambda hyperons, the sigma hyperons, and the cascades. We also mentioned in the meson sector also an octet of vectors with the rho mesons, the omega mesons, the k star and the k bar star mesons, and actually at the beginning of the lectures, even I mentioned a decuplet of baryons sorry, this is 1 plus, baryons 1/2 plus, and a decuplet of baryons with spin parity 3/2 plus, that you have the delta, you have the sigma stars, the cascade stars, and you have the omega star, right? Actually here, you have this state that it was predicted, and then the person who predicted the existence of this, got a Nobel Prize, right? Just by predicting. Yeah, I don't know if you know this thing. And in this decuplet, you have delta plus plus, you have delta plus, delta 0, and delta minus. I think I am going to use Italian technology instead of Chinese technology. And then this is 4 state. This is isospin 3/2, spin parity 3/2 plus. Here you have the sigma star plus, the sigma star 0, and the sigma star minus. Here you have the cascade star plus and the cascade no, I think it's cascade star 0 and cascade star minus, and here you have an state 3s. So, okay, so you see you have 4, 7, this is isospin 1, this is isospin 1/2, so 4, 7, and 2, 9 states that were in the decuplet, and there was one empty place that just using flavor physics, the content should be 3 strange quarks, and this is the omega, right? And it was predicted the existence of this baryon. I don't remember now the name. I think it was Gelman. No, it was Gelman, right? I am not sure in this one. It was Gelman. Gelman predicted existence and got the Nobel Prize for this, among other things. So that means that the SU3 vector symmetry more or less works, okay? So the idea is, okay, that if you have a field acting on the vacuum that produces an state, you have another field acting on the vacuum that produces a different state. I am repeating what we do, what we discussed yesterday. And then you have a transformation of this group such that U daga phi I U is psi B. Okay, so, is in this way or in the other way around? So then you can argue, okay, if I compute A, H0, B, A, that will be the energy or the mass of the baryon of this or the hadron A. This is okay. This can be written as A. Then I insert here U daga U H0 U daga U A. Okay, so then what I have is U. Then we say UA, right? Because if I take U daga here, I have UA, and UA is going to be, sorry, then let me put in this manner. I think it's better. So U daga is, UA is going to be U5A. Now I can put U daga U vacuum, right? So then U daga phi A U daga transform to the field phi B. Then we have U vacuum, right? And if U vacuum is again the vacuum, so we have the state B, okay? So then we come here and we say that this is B, U H not U daga B, right? And because U is a symmetry of my dynamics, this is again the Hamiltonian. So this is just B H0B. Okay? So then that's equal to EB. Okay, so that's the reason why we, in principle, all the hadrons that are included in these multiplets, they have more or less the same mass, right? Any doubt? But here there is a crucial point, which is this. Okay. This U is going to be, well, something like that. Okay, so then I will have a transformation that lives invariant the dynamics. So then I use Noether's theorem. There will be a conserved current, and with the conserved current, I can define a conserved charge that I call Q. And this Q is the generator of the transformations, right? Okay, then what happens with the axial transformations? We see in nature that, okay, the axial change the parity. So then there is an octet of light mesons with spin parity 0 minus, but we don't find the corresponding mesons, light mesons with parity 0 plus. There is a light octet of baryons where the rho lives with spin parity 1 minus, but we don't see the corresponding states with 1 plus, okay? And the same arguments for the nucleons. So then this blackboard cannot work. That is the Weyl, the Wigner-Weyl realization of the symmetry. Okay, there is something that is not working. And the thing that is not working is in here, right? In the Nambu-Goldstone realization of the symmetry, what happens is that U does not annihilate. U acting on the vacuum is not again the vacuum, so the vacuum breaks the symmetry. And the reason why the vacuum breaks the symmetry is because the corresponding charge does not annihilate the vacuum. Okay, a perturbative vacuum, if you are working with a perturbative vacuum, this will always happen. The charge will always, well, any operator will always annihilate the vacuum. So then we are in a situation where the vacuum, the ground state of the system, is very complicated and is highly non-perturbative. And this is what we are going to discuss next, right? Okay, this is just what we have discussed, right? That we have, well, in the slide, instead of talking about vector and axial, I introduce left and right transformations, and then is what I told you, right? That SU3 vector it seems to be satisfied, but however we have some problems, and actually. Then what we have is the important physics phenomenon of spontaneous symmetry breaking. That is the way that the axial transformation is realizing in physics, in QCD. Okay, so let me just put a typical example that I am quite sure that you have seen in the past. Okay, suppose that I have n fields, phi 1, phi 2, up to phi n. Okay? And suppose that I have this Lagrangian. So then this the potential that I have is mu square over 2 phi square plus lambda 4 phi square square. Okay. So what is my symmetry here? I have symmetry under rotations, right? Because everything are scalar products, right? I have psi is at the structure as psi squared, d mu psi, phi squared. I have d mu 5, or I have phi squared, or I have phi to the 4. Okay? So what happens is that if I go from phi to phi prime, which is just a rotation, okay, this is a rotation in n dimensions, then the Lagrangian is invariant, right? Okay, so let's suppose that the parameter mu is greater than 0. Then if the parameter mu is greater than 0, you could just minimize this potential, and then you just minimize this potential, and then you have something like that. Okay, so then so the ground state of the system is the ground state of the system in the vacuum. I think that the value that the field takes in the vacuum is 0. Okay, but what happens now if we take mu square negative? Sorry. What happens now if we take mu square negative? if we take mu square negative, then if you draw the potential, then you get what? A typical Mexican hat, okay? You just find, so here I can do perturbation theory, etc. So this is a perturbative vacuum, no problem, right? But in this case, so I can quantize, I can quantize my theory using perturbation theory, and everything works. But in that case, what you have is you just, well, it's truly symmetric. Okay, so this is the potential as a function of 5. Okay? In the case that mu square is negative. Actually, the minimum value of the potential is minus mu to the 4 times 4 lambda, and the field that I will call V, vacuum expectation value V is going to be vacuum expectation value is minus mu square over lambda. Okay. So what is happening? The Lagrangian still is invariant under transformations of ON, right? But however, the vacuum is not invariant under transformations of ON. Actually, the classical value phi 0 is not a minimum. The minimums are these. Okay, so then the vacuum breaks the symmetry. This is what is called spontaneously a symmetry breaking. Okay, so typically what you should do is, okay, you just choose one particular of these vacuums, right? So you just choose one particular of these vacuums, okay? And then any other vector could be written in this manner. Okay. So here I have n fields, and now I have again n fields, which are n minus 1 high I fields and another field rho. Okay? Why? Okay. Can anyone tell me this element of group theory, this TI, this what they guys are? These are elements of the group ON minus 1. Why? Because I can do rotations between the first direction and the last direction. Okay, because here I have I have many minima depending on the direction, right? So I have chosen one. I have just decided that all the fields annihilate takes a zero expectation value in the vacuum except one, the last one, right? And that it takes the V, this value of the expectation value. So how can I construct any other field configuration? Just doing rotations between, for instance, between the first coordinate and the last one, or the second coordinate and the last one, or the third coordinate and the last one. So at the end, what I have is ON minus 1. Okay? So in this manner, I can reconstruct any field configuration. I always need to have involved, I always need that the last component should be involved because it's the only one that that doesn't have a non-zero vacuum expectation value, right? And then any other field configuration is just constructed in this manner, right? So doing rotations between one direction in the planes between one particular coordinate and the other always involving the last one. Okay. So then I can just rewrite my Lagrangian in terms of the new fields, in terms of psi I and rho, and then neglecting psi square, just to make it easy, the Lagrangian is 1/2 d mu rho plus 1/2 d mu psi I d mu psi I plus, and then the potential is minus mu squared over 2v plus rho squared minus lambda 4v plus rho to the fourth. Okay? This is what we have. Okay, so then what we see is that we have this rho field now, has mass, right? If you look at, I don't find any mass term for the psi I terms. However, this rho field is going to have mass, right? It's going to have mass because the mass is not going to be mu squared. Later we will see an example. You should look at the quadratic terms with rho. And here you have mu squared rho squared, but here also you have a term with rho squared. And then this combination is going to give you a mass for the rho field, right? And actually what happens is that if I change, if I move from the ground state with some fluctuation of the rho, the energy of the system changes. But however, I find in n-1 fields which are massless because I don't have any mass term for them. Okay? So I have n-1 fields which are massless. So that means that if I take into account any fluctuation of these fields, the energy of the system does not change, right? These are massless fields. Okay, what this number n-1 has on particular, right? I started with our ON symmetry, right? How many generators does this group have? So this group has something like n times n-1 over 2 generators. Okay? So for instance, in 3 dimensions, this number is 3 times 2 divided by 2, 3, right? If you have rotations in 3 dimensions, you need 3 angles, right? The Euler angles. In 2 dimensions, then you have 1, because a rotation in 2 dimensions is just defined by only 1 angle. And in 4 dimensions is whatever it is. And then, after this process of spontaneous symmetry breaking, then I am left with my symmetry group is not longer ON. My symmetry group is ON-1, right? So how many charges I have, or how many generators I have? Well, I have n-1, n-1, n-2 divided by 2. Okay, it's just the same equation, replacing n by n-1. So now if you had this number of generators, of conserved charges, and now you have this number here, you subtract these two numbers, and the difference is n minus 1. The difference between n, between your symmetry group ON and the symmetry that you are left is the difference is n minus 1. That corresponds to the number of massless fields that have appeared in your theory, right? So the message is that any time that you break a symmetry because of the vacuum, then there will appear massless fields, right? And how many massless fields will appear? Well, the number of the difference between the generators that you have broken. Okay. Okay, this slide that I think that we could discuss, we could go through it in the tutorials on the exercise. Is just the mathematical proof of that what is called Gorston theorem. This is the mathematical proof that okay, you have a symmetry, then you have a charge Q that is, I have a pointer, right? Huh? Okay, thank you. Okay, so you have a symmetry, you have a charge that is conserved, so conserved current, but this symmetry does not annihilate the vacuum, right? Then automatically you can prove that a PR, this is Gorston theorem, then a PR states with zero mass, massless states, which are called Gorston bosons, right? Which are called Gorston bosons. Okay, so the thing is that my symmetry SO3, okay, my symmetry SO3 vector cross SO3 axial, or you prefer SO3 left, SO3 right, okay, reduces to just ISO3 vector symmetry, right? Because you have a spontaneous symmetry breaking in the axial sector, right? So then, in this, so we have this this mixed realization where we have that the vector transformations these symmetries realize a la Wigner way, while the axial transformation is realized to the Nambu-Gorston, right? So then SO3 vector is still a symmetry, but in the axial, then what you have is that appear Gorston bosons. And these Gorston bosons are here, are the octet of pions, right? So then in the case of SO2, you have, in the case of SO2, then in the case of SO2, you have the 3 pions, pi plus, pi minus, pi 0, right? You have 3 pions. In the case of, which are, well, their masses are small, are of the order of 140 MeV. In the case of SO3, then as I told you, you have to include also the kaons and the antikaons. And also the eta meson, right? So the symmetry is not as good as before. Okay, but the next thing is, this is fantastic, is QCD. These are the symmetries of QCD, but I have written my QCD Lagrangian in terms of the quark fields, but I don't see quarks in nature. What I do see in nature are hadrons, right? So what's the point of all of this discussion, right? So it's useless. It's useless to, well, if I want to describe some phenomena at low energies, I should make a change of degrees of freedom. I cannot describe this phenomenon in terms of quarks and antiquarks. I should describe this phenomenon in terms of hadrons, right? So I am going to give you an example. And how can I use these QCD symmetries to construct the theory? So the simplest case is the linear sigma model. Okay, then suppose that you have a system of pions, right? And you want to write a Lagrangian involving pions because you want to compute amplitudes involving pions. You want to do pi-pi scattering, right? How do you do that? Well, this is QCD, okay? Because this is, I now that I have, well, if I have pions in good approximation, I must assume that NU is equal to ND, and more or less, I can assume that the mass, these two quarks are massless, right? So then I have, well, I have these charges, but I know that these charges are conserved, so they are not time dependent, and then they follow these commutation relations, okay? And then I know that pions have isospin, right? So then if I want to compute the commutator of the vector charge with a pion field, okay, this is automatic, right? Because if you have a vector, if you have a transformation that behaves like a vector, right, then automatically the commutator is just the structure constants, right? This is what you do for spins, okay? Very good. But now you have a problem, right? Because what is the commutator of the axial charge with a pion field? The commutator of the axial charge with a pion field, okay, so the parity of this thing should be plus, right? Because the parity of the pion is minus and the axial charge has parity minus, so this should be an object with parity plus. So it cannot be a pion because the pion has parity minus. So then I introduce a new field, the sigma. Okay, and then just to make the thing simpler, I say, okay, the sigma is going to be an isoscalar. And if the sigma is going to be an isoscalar, then automatically I have Qj sigma equals 0. But then I need to know what is the commutator of the axial charge with the sigma field. Okay, there is something that is called Jacobi identities. Okay, there is something that is called Jacobi identities. If I find it, I can make use. I can make use of the Jacobi identities. So I need to know this commutator Q5I sigma, and then the sigma is Q5. Let me put J. Here I have J in my notes. Then I have J, and the sigma is, for instance, I Q5 1 pi 1, right? And now there I can use Jacobi identities. If I use Jacobi identities, then automatically what I have is everywhere appears either or the anticommutator of Q5J, Q5-1, or the anticommutator of Q5 pi 1, which I have already defined, right? So Jacobi identities, well, is ABC plus BCA plus CAB is 0. Okay? So then I can use these Jacob identities, and then you just do it. It's very easy, and then what you find is that the commutator between the actual charge and the sigma field is just the pion field. So I have found how the pions and sigma commutate with the generators of my symmetries, of the vector symmetries and the axial symmetries, right? Then I can check, for instance, that this object, sigma squared plus pi squared, commutes with the vector charge and also commutes with the axial charge. Okay? So then if I want to write a theory involving pions and this new sigma field that I have introduced that is invariant under the QCD symmetries, so invariant under vector transformations of axial transformations, I think it's pretty clear that I should construct, it should be done of construct using this invariance, sigma squared plus pi squared. So, okay. So I have sigma squared pi squared with the derivatives because I need a kinetic term. Then, okay, I have sigma squared plus pi squared. I give masses to the particles, and then I can put as many interactions as you want. I can stop my expansion with 4 fields, but I can add more and more terms. Yes. No. You're totally right. It's not at the level of course, because I need to construct a theory in terms of hadrons, of the degrees of freedom that I see in nature. In nature, I don't see quarks. Only I see quarks at very high energies, right? Why? Because of the Goldstone theorem that I have discussed earlier, I know that there should exist 3 particles which are massless, 3 hadrons which are massless, right? And then I look at and they are isobectors, right? Because I know that they should the particular behavior with the vector transformations. Then if I look at the experimental hadron spectrum, the lightest particles are the pions. So these pions should be the results of my symmetry, the spontaneous symmetry breaking, right? This is, but you have mentioned something that is very important. I am doing an effective theory. And the price that I am paying because I am doing an effective theory is that I have unknown constants, right? When I have in QCD is a fantastic theory. In QCD, everything, well, you have the quark masses are some unknown parameters that you cannot fix, and you have the coupling, but everything is fixed, and I can renormalize. I haven't mentioned anything about renormalization and anything, but this is in QCD, besides the masses, you have only one parameter, which is the coupling constant, and lambda QCD, right? That tells you the running. But here I am doing an effective theory, and a theory where the degrees of freedom hadrons are not quarks. And then I am paying a price. I don't have idea of what this coupling lambda is, right? And then I have here dots. If I want to include more and more terms, then appear more and more undetermined parameters, right? This is the price that you pay when you are working with an effective theory. I don't know if I have addressed your question. Thank you. Okay, so you understand that you have constructed your first effective theory using pions and just relying on the QCD symmetries. Okay. Then I can't easily, because I know, okay, these sort of things tell me how the pion changes when you do a vector transformation, right? Because, okay, you do a vector transformation and then from pi you go to pi prime. Okay, this pi prime is going to be 1 minus q theta pi, right? I do an infinitesimal transformation, and then I can use the commutator. Yeah, I can use the commutator, and then, okay, this is at the end of the day, this is just pi. Okay, pi, and then this is, okay, this is pi minus q theta pi. Okay, so this is, in Nether's theorem, this is the variation of the pion field. Then I can apply Nether's theorem, and then you get the vector current. Then the vector current is conserved, right? Because if you do d mu v mu, then automatically you get d mu pi cross d mu pi. This is the vectorial product, is 0. And then you have a term which is pu, which is pi times d mu square pi, right? So if you do d mu b mu, then you have d mu pi cross d mu pi plus pi cross something like that. And this operator is d mu, okay? This is obviously 0 because it's a vectorial product. And then why the second is 0? No, this is not massless. I have a mass. I have a mass. But you are in the right direction, right? Because you use the field equations. This is going to be proportional to the mass that I have given here times pi, and then pi cross pi is 0. So the vector current is conserved, okay? Then in the same manner, you can have the axial current. The axial current is conserved. And then, okay, you have an effective theory, but it's an effective theory that is not consistent with phenomenology. It's not consistent with phenomenology. Why is not consistent with phenomenology? Well, because I have that the sigma has the same mass as the pion, is this object here, mu squared, and I don't see in nature any 0 plus state with the same mass of the pion, so this is not consistent with phenomenology, and also because in this theory, the pion is stable, right? The pion does not decay, right? Because you could compute the matrix element of the axial current between the vacuum and the pion, and then you just get 0. And this is the definition on F pi, right? Yeah. No. No. They are generated here, and are generated because because pion and sigma fields, they should appear in the combination sigma squared plus pi squared. Now I am going to break the symmetry, right? But I mean, this is the key point. So what I have found is that, okay, I want to construct a Lagrangian that is invariant under separate vector and axial rotations, transformations, right? So then the invariant that I have found is sigma squared plus pi squared. So then I can put as many terms of the form sigma squared plus pi squared, okay, in my Lagrangian, because if I use this invariant, then my Lagrangian is going to be invariant. But then I am paying a price, right? Because both hadrons have the same mass. I don't know if is it clear? Yeah, they are not massless at this point, right? And also there is the point. There is the point that F pi in this theory, which is the pion decay constant, will be 0. Okay. So I have to do something. I have to break the axial symmetry. I should. I am just rewriting the same thing. just using some notation that probably, I mean, I can rewrite the same Lagrangian. I can rewrite the same Lagrangian just introducing these 2 by 2 fields, okay? And then the same Lagrangian it can be written just in this manner, where these traces are traces in the isospin space. And that's what I was telling you about the how the pion field transform and how the sigma field transform, right? And actually here, okay, here excuse me, I should, that was wrong, what I was telling you, because the pion is an operator and then it transforms like a matrix, right? You have something in the left and something in the right. Okay, so actually what you have is, I did it wrong. So it should be something like 1 plus q tau, then you have pi j, and then 1 minus minus q tau, okay? Just assuming that tau is infinitesimal, and then I have made the expansion for the exponential, right? So these are all the elements. I will give you these slides, right, later, and that gives you all the elements just to get the currents and things like that. This is for vector rotation. This is for axial rotations, and the invariance and the vector and axial could be translated into invariance into left rotations and right rotations, but there is a particularity, right? I will come back to this later. I want to discuss, I think it's more interesting if we just discuss symmetry breaking again, right? So we have to do something, right? Because the previous model is not, phenomenologically, is not satisfactory, right? Because we don't have the sigma and things like that. Well, so then the idea is easy. What we need is one of the fields here, you remember where is the, one of the fields, here it was the third component, the last component of the n multiplet should take a non-zero vacuum expectation value, right? So then either the pions or the sigma field should take a non-zero expectation value, which is the candidate. The pion cannot be, because of parity, right? It should be the sigma that is an even parity. Okay, so I write, this is the same Lagrangian that I wrote before, but just in this matrix notation, right? Where I take sigma and pi. This is exactly the same thing. So this is d mu sigma, and then d mu pi, and the only thing is that, okay, I have done this business here where I am relating the parameter mu that appears here. You see that I relate this mu and lambda with the vacuum expectation value, B, right? So it's the same thing. Okay. So we have two situations. The mass, well, in this language, the mass of this field, the common mass of the sigma and the pion will be this object minus lambda v squared. Then if v squared, v is the vacuum expectation value. If v squared is negative, then the mass or the common mass will be positive. It will be this case here, right? It will be this case here, but we don't want that. We want the case where the mass is negative here, the common mass is negative. So in this notation, the thing is just to assume that b squared is 0, right? It's just to assume that b squared is 0. So let me, I don't want you to. So the only thing is that I have rewritten the same Lagrangian, but I have rewritten the same Lagrangian that we have in the previous slide. I have rewritten the same Lagrangian that we have in the previous slide. We have mu squared and lambda squared, okay? And then we have, well, we have the sigma and the pion field. Now I am rewriting this Lagrangian. Instead of mu squared and lambda squared, instead using v squared, the vacuum expectation value of the sigma field and lambda. And then the relation between is here, right? The vacuum expectation value, v squared is minus mu squared divided by lambda. Okay, so it's just the same Lagrangian. Okay, that's the reason why we have that if the vacuum expectation value is negative, is because the mass, this mass will be positive, this mu parameter will be positive, and then we have a Wigner-Weil scenarios, right? So the interesting one is when the vacuum expectation value that takes the sigma field in the vacuum is positive, and then automatically we are in these Mexican hat scenarios, right? Okay, so then what we have is that the vector current still annihilates the vacuum, but however, the axial current does not. Actually, if you remember, the commutator of the axial current with the pion field was the sigma field, right? You remember that by definition, I introduced the sigma such that it was the commutator of the axial current and the pion field. Okay, so now I am assuming that the sigma is taking a non-zero vacuum expectation value. So this is not zero. So then automatically, because the pion annihilates the vacuum, then automatically means that the axial current cannot annihilate the vacuum, right? So then automatically we are in the Nambu-Goldstone realization, right? And now what we do is, okay, then we just go from the sigma field to this sigma hat field. And I introduce this sigma hat field just because that field, it will have zero value in the vacuum, right? And I can do perturbation theory with this sigma hat field. Okay, now you rewrite the Lagrangian. Now if you rewrite the Lagrangian in terms of the sigma hat field and the pion field, this is what you find, right? Broken generators. I had, at the beginning, I have O4 symmetry, right? Now I have only O3 symmetry because the sigma. Now in my new Lagrangian, I have only symmetry when I do rotations of the pion field. Then I have 3 broken generators. So then I should have 3 Goldstone bosons, right? I should have 3 Goldstone bosons. And then I read it here, which are the Goldstone bosons. I have just, I mean, it takes a little bit of time, but it's easy, right? It's the same Lagrangian in terms of the sigma and the pion fields that now you rewrite in terms of the sigma hat field and the pion field. And this is what you get. And it's just a matter of reading this. Okay. Do you find any master for the pion in this Lagrangian? No, there are no quadratic terms for the pions. So that means that the pions are massless, right? What about the sigma meson? There is a quadratic term for this new field. Okay, here. So I am giving mass to to the sigma. And this mass is just, well, the constant that I put at the beginning, and then it's proportional to the vacuum expectation value, okay, V squared. So then in this Lagrangian, I have massless pions, I have a massive sigma field, and I have a tower of interactions between the sigmas and the pions. Okay, so this is a typical example. And actually, now in this Lagrangian, now actually if you call, well, the vacuum expectation value, it turns to be the pion decay constant. Why? Because if you just compute the axial current is just, well, it was in the previous slide. You remember the axial current was sigma d mu pi d mu sigma pi. Sigma d mu pi. Okay, so sigma is sigma hat plus the vacuum expectation value that I call f pi, d mu pi, minus d mu sigma. So d mu kills the vacuum expectation value. So then you have d mu sigma hat and pi. And then with this axial current, you just compute the pion decay, and you find that really this correspondence is really correct. This is the pion decay constant. Yes. Okay. Okay. So just a final remark. In this Lagrangian, because I have that the vector current is conserved and the axial current is conserved, right? Because I have not explicitly breaking the symmetry. Okay. So we stop. 10 minutes. Okay, it's more or less, it's a bit, I don't know, how many of you have already seen these things of spontaneous symmetry breaking? Oh, but, in different systems, right? But I mean, I think this is the easiest place to see it, right? And then illustrate how to construct effective theories with the new degrees of freedom that you have, okay? Okay, very good. So we resume in 10 minutes. Okay, so I think that we resume, right? Okay, so then I just make a little summary that we have assumed that the sigma field takes a non-zero vacuum expectation value, V, and then automatically that automatically implies that the axial charge does not annihilate the vacuum. This is very important, right? And that's straightforward. It's just because the commutator of Q of the axial charge with the pion field, that was my definition of the sigma. I introduced the sigma in that way. So then automatically, this matrix element is proportional to the vacuum expectation value of the sigma field, which is not zero. And then that automatically implies, because the pion annihilates the vacuum, just because quantum numbers, that automatically means that the axial current should not annihilate the vacuum. So then you have a spontaneous symmetry breaking, okay? And then you can construct your theory. And then in your theory, you have at this level 2 parameters, this vacuum expectation value and this parameter lambda. With this vacuum expectation value and this parameter lambda, you just give mass to the perturbative sigma, right? Because here I have shifted the sigma field just to make sure that this new field annihilates the vacuum, and I can do perturbation theory with this sigma hat field. And then I give mass to the sigma, and then I can explain the pion decay. So I can explain I can compute this matrix element, and this matrix element is going to be proportional to the vacuum expectation value, and then that's the reason why I have called it F pi from the very beginning, right? 2 parameters. But in the effective theory, it can include more and more, right? Parameters, right? Which is the main difference with QCD. Right? In QCD, the QCD is a renormalizable theory, and then I can compute as many loops as So you did as many loops as you are powerful to do, okay? And then you don't get any new constants. Everything is reabsorbed into the core masses, which are unknown parameters, and into the running of the coupling constant. Okay. A different issue is that depending of the regime, you are very strong and you compute many loops, but the series doesn't converge, right? And this is a different problem. Okay. So, okay. But then you could complain. Juan, you have introduced a perturbative sigma field that it has a mass. But I look at if I look at to the hadron spectrum where this sigma particle is, right? So from the phenomenological point of view, you still have a problem, right? And that's the reason why people don't use the linear sigma model. Use something more complicated, which is the non-linear sigma model. In the non-linear sigma model, you don't need to introduce a new particle. You don't need to introduce the sigma. Okay, so the only thing is, you remember, the only thing is that I need to define the commutator of the pion field with the axial charge. In the sigma model, I assumed that the commutator of the pion field with the axial charge was proportional to the sigma field. Remember? Okay, now I want a theory that involves only pions, only pions. So what I do is, okay, it's going to be some function of the pions field. Okay, because I have two indices, then these objects will have two indices. And then the more general tensorial decomposition of this object is just the delta, the Kronecker delta, and then pi j, pi k, because I have O3 symmetry, okay? But then I don't know F and I don't know G, okay? Good. But now I can use the Jacobi identities to find I can use the Jacobi identities to relate I can use again the Jacobi identities as I did before to find a relation between these unknown functions F and G. And again, it's something that in the tutorial lectures we can say, okay, I want just to get this relation or other relations, and we do. And it turns out that there exists this constraint that G and F are related by this constraint. Okay. So the usual choice is to assume that f pi, this function f, is just the square root of f pi squared minus pi squared. Why? Because if you do this thing, it turns out that twice f prime is -1. And then the g function is 0. That makes your life easier. You just say that Q, the commutator of the axial charge with the pion is just minus I delta jk and a function f pi, which is f pi squared minus pi squared. So that will be our sigma field. And actually, automatically, we realize that this takes a non-zero expectation value in the vacuum, right? Because the pion is going to be perturbative, but then when you just this matrix element in this relation here, when you compute the matrix element in the vacuum of this commutator, is going to be just f pi, right? Because the pion field is going to construct. Okay, so then automatically have a theory that only involves pions, which is, just in practical terms, is a theory that you will, well, suppose, well, it's the same theory that I have here, and suppose that you replace sigma by this highly nonlinear realization of the, or in terms of the pion field. And this is the reason what is called, this is the reason what this is called the nonlinear sigma model. Okay. Then typically, so then I think that this moment that I should come back to this slide here. Okay. Typically, those who have already worked in carrier representation theory is carrier representation theory. Typically, people work in terms of matrix in the SU2 and SU3 space. And one of these matrices, well, is typically you work in terms of a matrix in a 2x2 matrix that contains the neutral pions, the charged pions, and the negative, the positive charged pions and the negative charged pions. Here there is an issue. I mean, to now I have been working with Cartesian coordinates, right? I have been working with Cartesian coordinates. I have been working with P1, P2, and P3. I have been working with 3 real fields, right? But now in nature, what you have is a neutral pion, and then you have the pi plus and the pi minus. Okay, so I don't want you to get lost, but the idea is that you pass from these Cartesian coordinates, you pass to spherical coordinates, right? So in the spherical coordinates, the pi 3 becomes the field of the neutral pion, right? Because it doesn't have charge, so it could be just represented by a real field. While instead of pi 1 and pi 2, then you have I think that you have pi plus, I think it's something like that, pi 1 minus I pi 2 divided by square root of 2 or something like that. I am not sure about this sign, it could be plus. But then this new field is complex, and then you know in quantum field theory that a complex field creates the particle and its antiparticle. And so then this annihilates positive pions and creates pi minus, right? So the field that annihilates pi minus, it will be, the dagger of this field will be something like I pi 1 minus I pi 2 square root of 2 or something like that. I was telling you this thing just to notice that instead of pi 1 and pi 2 here in this matrix, I am just writing pi plus and pi minus, right? They are the proper combinations, okay? So the Lagrangian that I wrote at the beginning, this Lagrangian, it can be written in matrix form in this way, right? In the same way. So you can just check it. And then the thing is, okay, I now have the pion, and in this case, the sigma transform and the vector and axial. I am just to make it easy in the linear sigma model. I now have the pion and the sigma fields transform under a vector and axial rotations, right? And then the question is, okay, if I introduce this matrix field sigma, how this field transform under a vector and axial transformation, right? And then you can find out that under a vector transformation, you have that the sigma transform like GB dagger. And then you could check that trivially things that involve the trace of 2 sigma matrix fields automatically is invariant, right? Because you have a trace of GB sigma GB daga, then you have GB sigma GB daga. This is 1, and here you have the trace of GB sigma GB daga, right? And then because you have a trace, you can move the GB daga to the first place, and then you get trace of sigma, okay? So the people use these matrix fields because it's much easier to write terms which are invariant and the vector and axial transformations, right? So all of these terms are well, all of these terms are invariant. Then if you do an axial transformation, what you have is, if you have, well, it's the same, well, it's here in the slides I put sigma daga, but it's correct because sigma daga is the same, right? If you put the daga operator here, you get again GB sigma daga GB. So what they have done is correct, right? What they have done is correct. Why should I put sigma daga? Why was a big mistake writing sigma? Can anyone tell me? Well, the thing is that sigma is not Hermitian. Yeah, Hermitian, right? So that's the reason why this should be sigma daga, right? Okay, because if you have trace sigma, you take daga, then you have trace sigma daga, which is not Hermitian, right? However, you have trace of sigma daga, then you get sigma daga, it's Hermitian, right? So that's the reason, but it was a big mistake just putting here sigma. But the idea is the same thing, right? Sigma transform like GB, sigma GB daga, and then sigma daga, if you take the daga operator here, then sigma prime daga is going to be GB, sigma daga GB again, right? So it works. Okay, wow, but in the axial current, if the slide is not mistaken, it seems different, right? Because instead of GB daga, what you have is GA is the axial transformation. What you have is GA daga. What's wrong with that? Is it still invariant or not? Eh? It is still invariant, right? But then, okay, I am going to show you that it's still invariant, right? Because the only thing that happens is that I am going to have here GA daga, then I am going to have here GA daga, and then now I am going to have GA. And again, I move GA here, it's still invariant. So then, it's very easy to see that this Lagrangian written in terms of the matrix field sigma is both invariant under vector and axial transformations, right? Good. And then, but if you look at any chiral perturbation theory paper, they never talk really about vector and axial transformations. They talk about left and right transformations, right? Left and right transformations. So you remember a left transformation, it was just B minus A and over 2, and a right transformation, it was just B plus A over 2, right? So then you can show that that this sigma matrix field, when you do a left-right transformation, becomes GR, sigma, GL, dagger. And these GR matrices in the SU2, in this case, fields. And again, it's easy to see that is invariant under left and right transformations. This is, we can do it. We can do it. So then we have trace of sigma dagger. Then if you do a transformation, it becomes a trace of GR sigma G dagger left. And then sigma dagger will transform like GL. So if sigma transform like G right, sigma G left, sigma dagger will transform like GL, sigma dagger G right dagger. So now it's going to be GL, sigma dagger, and then G dagger right. So this is one. And then because I am inside of a trace, I can move G dagger R, and then it's invariant, right? So it's, well, it's equivalent, right? So this is, I mean, you could see very easily that you are writing Lagrangians, which are chiral invariant. In the sense, chiral invariant means left, right, or vector axial. And then you can construct a whole tower of things, okay? And what I have seen here, suppose that this is for the linear sigma model, but suppose that is also for the nonlinear sigma model, but here you have something more complicated instead of the sigma, right? It's a function of the pion fields. Okay. Which is what I am writing here, right? Instead of, okay, so typically, well, I was talking about this sigma field in the literature. You may find also this U field. Okay, so this is a very funny, right? This is a very funny. Have you ever talked about reparametrization invariance? You know what reparametrization invariant means? No? Eh? Yeah. Okay, now I am using, okay. What I am doing is the following, right? So I have introduced this object, psi squared, okay? I have introduced this object, psi squared. So I have f pi over the square root of 2, and then this object psi squared is f pi square root of 2, and then is e to the tau phi f pi. Okay. Now, if I do this thing, this is f pi over the square root of 2, and then I think this is cos 5. This field here is going to be, let me get all the factors correct. Yeah, it's going to be cos f pi plus I tau 5 over 5 sine 5 pi. Okay. And 5 squared is just 5 squared. Okay. So the thing is, well, this is a bit subtle of quantum field theory. Okay. Suppose that you want to describe pion interactions, right? And then you start with a mathematical representation of the field that you are going to use to describe pions, right? But then, okay, you say, is the physics is going to change if I redefine the field that I want to consider to describe pions, right? Because here, I mean, you see this thing, you, the relation is something like that the pion, so you remember before it was sigma plus I tau pi, right? So now the pion is going to be something like, the pion is going to be something like this field. Okay? So the physics, and now I say, okay, I am going to use this field 5 to describe my pion, right? So the physics could depend on my mathematical choice of the fields, right? As long as, because I am doing perturbation theory, as long as, so then in general, what I have is that I pass from pions to some function of the pion field, and then as long as for small fluctuations, this complicated and nonlinear function is 1, as in the case, the physics cannot depend. I mean, the perturbation theory cannot depend if I use the mathematical representation of the pions in one way or in another, right? It cannot depend. Why? Because look at the difference between this and this is higher order. So if you just invert this thing, you will find that the pion, I am doing a redefinition when you have pion and then you have plus order 5q or whatever it is. So it's higher order in, in perturbation theory. But at the end of the day, I need to fine tune. Okay? So then typically, people working in KPT, we use this representation for the sigma matrix in terms of this new field, 5. And then automatically we are implementing this because you can check that this is the square root of f pi squared over 5 squared. And this is the nonlinear representation of the sigma model. Okay? We can do a tutorial on this if it's not clear. Okay, so then this is an example. This is an example. I can just do pion scattering. And here I have just one parameter, which is f pi squared. And then I can compute pi plus pi naught going to pi plus pi naught. And then this is the amplitude. And then I have only the pion decay constant is my only parameter, because in here I am just in here I have not include the pion mass. I have with a theory where I don't have break the symmetry. Okay. So this is a prediction that Weinberg made. But this Lagrangian, okay, is okay. So U contains all the powers of 5, right? U contains all the powers of 5. Here I have just stopped the expansion to order 5 to the 6. Okay, but I can include more and more and more terms. So it means that I have, well, in this Lagrangian, I have 2 pi going to 2 pi. I have 2 pi going to 4 pi, etc., etc. This is the virtue of the nonlinear sigma model. Though life is not so easy, right? Because you do 2 pi to 4 pi, I can write other terms that also will contribute. I think that we will get this thing, and then tomorrow in the blackboard, and then we will compute this matrix element, and then you can compute cross sections and things like that. Well, here it's important to realize that the interactions of the Goldstone bosons are always derivatives, right? So you see that appear always the derivatives of the fields, right? So soft pions do not interact. Have you ever heard about that? So this is T. The T is the Mandelstam variable, but I want you to see the Lagrangian. The Lagrangian is proportional to the derivatives of the pion field. And all the terms in the expansion, all the terms are proportional to the derivatives of the pion field. So if the pion is soft, and soft means that it has zero momentum, the pion does not interact. Pions are free. Okay? Right? So far, the pion doesn't have mass. Okay, I can include a master, but a master for the pion will break axial symmetry, right? So this term here, I have, okay, how can I include a master for the pion? How can I include a master for the pion? Okay, look, I have put here the trace. I have include here the trace of CU dagger plus U C dagger. Okay, and C is twice B naught and MU00MD. Okay, so suppose that the U quarks, the U and D quarks, they are not massless, but they have the same mass. Suppose that they are not massless, but they have the same mass. Okay, and then I do a vector transformation of this piece of the Lagrangian. If I do a vector transformation, I remind you that U goes to GB U GB dagger. Okay, so now this term is going to be psi GB dagger U GB plus U dagger is going to be GB U. Sorry, this is U dagger, and this is going to be U dagger is GB, U dagger, GB dagger, and then now it's going to be GB, U, C dagger, GB dagger. I have done a vector transformation. It's invariant, this term. So I have done a vector transformation, so then U dagger has become GB, U dagger, GB dagger. And U has become GB, U, sorry, GB dagger. Okay, excuse me. Is invariant under a vector? This term is invariant, or I have broken vector symmetry? Because I want to give mass to the pions without breaking vector symmetry. It is invariant or not? Exactly. This is the point. If the masses are equal, the mass of the U quark and the D quark are equal, then, as you said, the GV commutes with the chi. Then I can move this GV here, and because I am in a trace, I have GB dagger. It's 1. So then I am not breaking vector symmetry. Okay? What is happening? What happens with axial symmetry? Of course, if I have different masses for the U and the D quark, I am breaking vector symmetry, because then the GB will not commute with chi, okay? What happens with axial symmetry? The only difference with axial symmetry is that if I have an axial transformation, I have GA dagger, U, J dagger, right? So what happens here is, okay, so this is going to be GA, this is going to be GA, this is going to be GA dagger, and this is going to be GA dagger. I am breaking axial symmetry, because now even if I commute GA and chi, then I am going to have, even if I commute, I am going to have trace of GA, chi, U dagger, GA. Okay? I can take this GA at the beginning because I am in a trace, but I have GA squared. This is not 0. So then I am breaking axial symmetry. So I am just putting a term in the Lagrangian that is consistent with vector symmetry, but I am breaking axial symmetry, right? And that gives a mass to the pions, right? Because look at this is F pi, square root of is 2 square root of 2, and then you have the trace. You just keep linear terms, quadratic terms. You just say that e to the I tau 5, you just keep quadratic terms, and that gives a mass to the pions, right? Sorry. Well, it depends. If I assume, okay, if I do S of 3, then I will have this, mu, and d, and s. If I assume that the strange quark mass is equal to the d quark mass and the u quark mass, then I will have S of 3. But it's the same thing, right? But the symmetry is going to be much poorer, right? Right, because the strange quark mass is much different. Is different to the up and down quark masses, right? But the key point is that I want to give masses to, right? Because I mean the pions are Goldstone bosons, and then Goldstone bosons means that in the limit of massless quarks, they are massless. The pions are massless, right? And I want to give mass to the pions, to this Goldstone boson, these Goldstone bosons in such a way that they preserve vector symmetry, and in such a way that the mass is proportional to the mass of the quarks. Right? If the quarks are massless, automatically the pions become massless again. And then here I have a constant. Here I have a constant, B0, right? And it's an unknown constant, right? In an effective theory, you have a series of unknown constants. Actually, one of the problems with effective theories is the following. One of the problems with effective theories is, okay, it's fantastic. We have computed this 4-pi diagram, right? We have computed this 4-pi diagram. I have done the leading order, which is just this trace d mu u d mu dagger. I have computed. Even if you wish, you can include the mass terms, and then this diagram becomes t minus m pi squared. This is the contribution that you get from this term, divided by f pi. Okay, but you want to do loops. Okay, you want to do loops. So now you see, okay, so I can do something like that. Okay, so then this term is order 1 over f pi squared. This term here is order 1 over f pi to the fourth. Why? Because I have 1 over f pi squared here and 1 over f pi squared here. Okay. By the way, when I told you that soft pions don't interact, is if they don't have momentum, and then you neglect the masses, right? Because you see the pi-pi interaction is proportional to t minus m pi squared. T is a function of the momenta, and then you have m pi squared. Okay, so I don't know how much you know about computing loops and things like that, but there you compute this loop, it diverges. It has an ultraviolet divergence. Okay, it has an ultraviolet divergence. And then this is something important that in QCD, you just compute loops and you can renormalize all the loops because all the divergences can be subtracted just by your constant, but the constant you have originally in your Lagrangian, right? By just renormalizing the masses of the quarks and renormalizing the coupling constant, right? Because it's QCD is a renormalizable theory. But an effective field theory, the situation is much worse. What happens is that you have infinites, and then, okay, you say, okay, maybe I can just renormalize my theory just by modifying the parameters of my theory, just by renormalizing the pion decay constant and the pion max, right? Just doing an expansion. So, okay, what I have is that f pi squared is going to be something at first order plus some expansion in powers of f pi or whatever it is, right? And the same thing, and you can renormalize the pion mass. It's not enough. You could not reabsorb all the infinites just by renormalizing the constants of your leading Lagrangian. You need to include new terms. You need to include new terms. Directly, new contract terms. So new contract terms means terms in your Lagrangian with 4 derivatives. So there will be, so I have the leading order is d mu u trace, but then why not? I can have d mu u, d mu u, d rho u, d rho u. This is another term that I have. But I have 4 derivatives. So I am doing an expansion in powers of derivatives. And then you need to include this term to make your amplitude finite. Okay, but the constant in front is totally arbitrary. So you just, in an effective theory, you have an infinite tower of interaction terms with coupling constants that you don't know the magnitude, right? You could say, okay, I can determine sun in the experiment, or I can determine sun in lattice QCD or whatever it is, but this is really a big problem. So this is the major limitation of effective field theories, right? That you have an infinite tower of conductors. But there is a power expansion, right? I am doing a counting in the number of derivatives. Any derivative is going to bring down a pion momentum, right? So then if you are very close to that some threshold, then you could think, okay, that this series is going to converge. Okay, so we have only 2 minutes, and then I would like to, I think that we should finish this first. Okay, we have also baryons, right? So far, we have only done a theory with pions, right? So in the spectrum, in the hadron spectrum, we have also baryons. So the most easy thing is to have a model including pions and nucleons. right? This is this is thing. Okay, so then I look at the spectrum and I see that the lowest baryons are neutron and proton, and they are an isospin doublet. So then I can introduce a field representing the neutron and the proton. Any problem with that? Any problem with the second? Now I need to guess how nucleons, how neutrons and protons behave when you do a vector or an axial transformation, right? Because the idea is always the same. I want to find some quantity that is chiral invariant, and then I want to construct a Lagrangian in terms of this quantity. The mechanism is the same. I want you to, this is complex because chiral Peterson theory at the end of the day has a lot of mathematical apparatus, but the idea is always the same, right? I think that this is pretty clear, right? This is a isospin rotation. No, what you have is look, what you have is just a proton and a neutron. Now you put here an SU2 matrix, and here you have this is the transform field, and this is the original field, right? Agree? This is trivial, right? Any doubt about that? This is just saying that the neutron and proton have formed an iso doublet, okay? Axial, I have to put gamma 5. That's what they did for quarks, right? That's what they did for quarks. Okay, so the point that I don't have time is to show you that this quantity here, which is just sigma bar, so is this bilinear, sigma bar, and then I have here sigma hat psi, and this sigma hat is e to the I gamma 5 tau 5 divided by twice f pi. Okay. The key point is just to show that this is chiral invariant, that this quantity is invariant when you do a vector transformation or when you do an axial transformation, right? This is, it takes a bit of time, but this is the key point, just to, yes, I am finishing, thank good. And then automatically without the 2, right? Because this is this b squared, and b has a 2, it's b squared. So this quantity is chiral invariant. And then if this quantity is chiral invariant, then automatically here I have a Lagrangian involving pions and nucleons, which is chiral invariant. Right? Because you remember the gamma mu when I do left and right transformations, so vector and axial is invariant. Okay, so this is chiral invariant. I have many problems because I don't see any mass term for the nucleons, and the nucleon mass is 1 GeV, right? I have problems, but it's not so much difficult because this field involves the interaction with my pion fields, and then okay, the spontaneous symmetry breaking of the axial current is going to provide you mass for the nucleons, right? Perhaps tomorrow we will spend half an hour on this. Okay.